where we are in the semester. Oh my goodness. So project part 2 grades are out. So get your complaints ready, I guess. I'll field any complaints you have, I guess. But grades are out. There's 2 separate grades. For a lot of you, this isn't relevant, but just for those of you who are, it is relevant for. Oh my goodness, my sentences. There's the 3 objective grades that are your team scores. I distinguish between score and grade in these. So those are your team scores. That's what the project itself that your team produced. That's what you got on each objective. That's how your project was graded. And then there's your actual grade or the number of AOs that you earned. And that can be adjusted. I do the individual grade adjustments. Well, actually, not even surprising, but a lot of you lost points, for example, not filling out meeting forms. Like, come on, that's one of the things that you're asked to do on the project, and I thought I made that super clear. Just a reminder, these are the 3 big things that I'm looking for doing individual grade adjustments. If you got an individual grade adjustment, you, in the negative direction at least, you probably just ignored this or didn't even read the document. I don't know. If you're not even filling out the team eval forms, it's hard to have too much sympathy if you can't do that little tiny amount of work. I know some of you just forget, but I don't know. But just a reminder, I do go through these 3 things and make individual grade adjustments where I feel necessary. Again, I'm not surprised, but how many people don't bother filling out the team eval forms is not 0, which would be the only thing that would be acceptable. All right. Any questions on anything before we get into it? I don't want to dwell on project. The project stuff, it's all, by team, by individual. There's not much I can say that applies to everybody, but I just want to throw that one thing out there. Are there any ways for us to increase our project 2 grade? No. Like how the late deadlines? No. Projects part 2 through 4 in the presentation, it's all AOs. The only reason there's multiple deadlines, there's 3 separate deadlines for everything else in the course. The only reason for that is because you need every learning objective to pass the class. So I want to give you opportunities to show that you did learn the stuff, even if you didn't learn it at the time you were supposed to. I still want you to be able to make up the learning objectives to be able to pass the course. Then I have AOs as an incentive for you to do it earlier, when you're actually supposed to do it, instead of relying on the late deadline and, God forbid, the final deadline at the end of the semester. If you're relying on that one, oh my goodness. Some of you, for good reason, have to rely on that. That's why it's there as a safety net. But there are some of you who did not submit homework too, even at the late deadline. My goodness, one little mistake and you just failed the course. I don't know why you're putting yourself in that situation. But and those students probably are the empty seats, so I'm talking to nobody there. But that's the reason why there's multiple deadlines, is when it's a learning objective, I'm saying you need to learn this stuff to pass the class. It's literally learning objectives of the course. This is what I need you to get out of 312. So if you don't get all of that stuff out of 312, I'm not letting you pass the class, but I'll give you all these extra chances to do that. Project parts 2 through 4 and the presentation, it's all AOs. That's where you're earning your A's, so to say. No, you don't get second chances on that. It's one and done. Just like all the homeworks would be if it was percentage-based grading and I didn't have this wacky grading structure, everything would be one and done. You would have a homework 1 deadline, a homework 2 deadline, no way to make up any points. So no, there's no way to make up points on project part 2. And a lot of the, I will say a little bit about the project. A lot of the mistakes I saw were things that were pushed on the 22nd, the night before the deadline, or the morning of the deadline on the 23rd. And then there's not enough time to properly test, and you realize you just submitted a completely broken project. That's what a lot of it was. That just last minute work and then not taking time to test. And I mean, start early. You've heard that a billion times. If you didn't listen yet, you're still not going to listen to me, but start early. And some of the security issues, I get that it's easy to make a mistake on the homework. You can accidentally have a security issue and say, man, I messed that up. But when there's a team of 4 to 6, how does that get past 4 to 6 of you? Even if it's 4, how does that get past 4 students? No, there's no way to make that up. 4 of you said, yeah, that's good, and you didn't escape HTML, for example. It's an easy thing to forget, but it's a hard thing for 4 people to forget. No, you don't get that back on the project. But yeah, I don't want to talk about it too long. But any other questions? I'll talk about it if there are questions. If not, I'm going to assume that everybody here has done what they're supposed to do and got good grades and is happy with it. Yeah.
Does today's lecture just cover the whole AO or no?
Not the whole thing. It'll be by Wednesday. So today's lecture, reminder, I'm done with the learning objectives for homework 3. All that's on the table. I got everything down. I have 3 slides of WebSocket refresher review today, and then it's on to WebRTC. WebRTC is AO only, and that's what I'm covering this week. And a reminder about WebRTC, I mentioned this last week, but that seems like a long time ago. Seems like it was a long weekend, for me at least. That WebRTC is something that I have a lot to say in lecture. I'm going to fill up these 3 lectures with all kinds of stuff about WebRTC. But when you go to actually code it, it's not that bad. It's pretty straightforward if you have your AOs done or your LOs done. I think the LOs for this assignment, it's just the way it kind of ended up coming out. I think the LOs for this assignment, I think each one is harder than the AO. So get your LOs done early. Give yourself a little bit of time to do the AO and get all 4 of these things done is my recommendation. Don't leave the AO on the table. But if you don't have your WebSockets working really well, including buffering, the WebRTC, the AO, isn't going to work because it relies on WebSockets. So you do need your WebSockets working nice to get the AO, and the AO is kind of a bonus, your little cherry on top. Good job getting all the learning objectives done. Here's your 2 extra application objectives. Is effectively how it worked out. Some of you will have AO-specific issues that you'll have to debug, but if everything else is working great, the AO shouldn't take too long. Well, let's get into it. All right, so WebSockets, we went over all last week. And starting 2 weeks ago, Friday, I guess. It's been a while. We've been talking about WebSockets. And just a reminder, we had a WebSocket handshake. We get an HTTP request, a request to upgrade the connection to a WebSocket connection. It contains a random key, and we need to respond with an HTTP response with a very specific accept. And then we're going to keep this TCP connection open by never letting the handle method, never letting that stack frame return, and keeping that on the stack. And that's going to keep that connection open. And then we're going to continuously receive stack frames in a loop by calling the receive method. To compute that key, or to compute the accept from the key, we're going to read the key. We're going to append this exact string to the end of that key. We're going to take the SHA-1 hash of that and then base64 encode the hash. And that's the proper accept. And this is where, I won't dwell on it right now, but this is where I encourage testing and writing your test cases for this to compute this. And then once the connection is established, in your while true loop, you're going to read from the TCP socket and expect WebSocket frames in this format. And if the payload length is large, you're going to start buffering to make sure you read the entire payload before you start processing the payload of that frame. So that's WebSockets. Very quick review. Any questions on WebSockets? I'd be happy to talk about WebSockets for a bit. If we get a 2 on the project part 1 objectives, is that 2 AOs or 1? Wait. If we get a 2 on one of the project 1, depends what deadline you're talking about. But the part 1 of the project, those objectives that you individually did, those are all learning objectives, so they behave the same as homework objectives. If you got a 2 or a 3, those are the same thing. You get credit, and if you did it by the project 1 deadline, 2 or 3 is 2 AOs, and by the project 2 deadline, which we were all busy grading project part 2, so we'll get to project part 1 Unfortunately, we are a little late on those. I forgot that I have 2 deadlines at the same time that the TAs and I just don't have the bandwidth to get all of that graded in 1 week, especially with individual grading. That's what I did all day yesterday. It sucked. But the project part 1, if you got it by the project part 2 deadline, it's 1 AO whether you got a 2 or a 3 on the objective, per objective. Part 2. Oh, well, that's a completely different question. On part 2, they behave differently. A 2 is 1 AO and a 3 is 2 AOs. So it's at most 6 AOs if you got 3s on all the objectives. But like 2 3s and a 2, that's 5 total AOs. So the grading for AOs is different. Again, this is where you're earning your A. You got to get the 3s at that point. The reason a 2 is considered complete for the learning objectives is because it is pass-fail. Like literally the whole course hinges on that. If I'm saying you got to get 3s on absolutely every learning objective, I just think that's too high of a bar. You can have some mistakes. If you get a 2, that means things mostly worked but were buggy. I think that's okay for a learning objective in order to pass the class. But for application objectives where you're really earning that A, you got to get the 3s. Why on the homework, even though there's no difference grade-wise between a 2 and a 3, we still give you that feedback. We let you know, hey, this is a 2. You have credit. Don't worry about it, really. But this is what a 2 is. So by the time you get to project part 2, you should understand the difference between a 2 and a 3 because you have all the feedback on the homework assignments. That's the intent, anyway. So you know what a 2 is, you know what a 3 is, and then by the time it matters, you do understand the difference. That's the intent. Whether it comes across that way or not, you can let me know, give me feedback so I can improve it next semester. But that's the intent, is we give the feedback on the homeworks, and then project part 2 is the start of when it matters between a 2 and a 3. Which actually, given that, the AOs on the homework assignments, now that I think about it, probably should be difference between a 2 and a 3. And then WebSockets, for the payload length is either 7 bits, 16 bits, or 64 bits. And you have to read that 7-bit value to figure out which one of these 3 cases it is. And masking, if you're reading messages, reading frames from the client, there's a 4-byte mask. And when you're sending frames from the server, there is no mask. You don't mask your bytes. Okay, now it's the end of WebSocket review. 4 slides. I thought it was 3. I added 4. Okay, WebRTC. This is Web Real-Time Communication, WebRTC. This is a way to establish a live streaming, I should probably hyphenate that, I don't know. A live streaming peer-to-peer connection. This is what we're going to establish with WebRTC. And we're going to use this for video and audio. So we're going to have basically a video chat service using WebRTC. This is fairly new. Stable release in 2018. All the major browsers since 2018 have been implementing WebRTC, but just something to keep in mind if you're building an app that uses WebRTC, anyone who doesn't update their browser and has a fairly old device or whatever the situation, some people are still running Windows XP out there, they're not going to be able to use your WebRTC. So just keep in mind that this isn't going to work for every one of your users. If you're a huge corporation like Facebook or Amazon or something, like they can't push out WebRTC and just guarantee 100% that all of their users are going to be able to use it, just because it is newer. But most of your users are going to use it. And if you're okay not having the Windows XP user use your site, that is what it is. Amazon probably cares because they want everybody spending money on their site. But they don't really need WebRTC for anything they do anyway, I guess. I don't know. But anyway, just keep that in mind. Stable release in 2018. And the good thing about this, for us is that most of the functionality is built into the browser. This is really the browser's implementing WebRTC, and that's why I say, like, I have a lot to talk about. Like, I'll explain WebRTC for a few lectures here, but when you go to code it, there's not much for you to code because the browser is doing most of the work. So that's why WebRTC is just kind of easy to code, because it's all browser stuff. And I'm not going to change this course to re-implementing a browser from a TCP socket. I'm never going to go there. So the browser, we just use all that functionality built into Chrome and Firefox and have our server do whatever the server has to do, which is what we'll talk about. So WebRTC establishes a live streaming peer-to-peer connection. Let's piece this sentence apart and talk about what this actually means. What's a live streaming peer-to-peer connection? And let's start with peer-to-peer. Peer-to-peer means exactly what it says. Peer-to-peer, what this means is that two clients are communicating to each other directly without a server, which is another reason why our job is kind of easy to code for this, because servers very lightly involved with the whole thing. Once the connection is established, in fact, our server has no part in this. It's a peer-to-peer connection. What's a server doing in there? Nothing. Nothing for a peer-to-peer connection. What we're going to code is establishing the connection. We're going to help negotiate between the clients and have two peers be able to negotiate with each other to be able to say, yeah, let's start a WebRTC connection. So our server is going to have to negotiate that. And then once the connection is established, our server says, my job here is done, steps out of the way, and then it's a true peer-to-peer connection. So if you're into serverless architecture, WebRTC is one of those technologies which still kind of needs a server to get things going. But once it's established, it's peer-to-peer. There's no server involved. There's no one spying on your data except your ISP. They can still see it. But as long as everything's encrypted, they can't see what you're doing, just who you're talking to, and you can have peer-to-peer connectivity. WebRTC is live streaming. Live streaming. We use streaming, even live streaming, quite a bit these days to mean a variety of different things. So just being very particular about what I mean by live streaming is important here. So live streaming, I mean real-time streaming. Real-time streaming, meaning that I want to talk to another person with end-to-end delay being absolutely critical. If you've ever had a chat with somebody, probably using not WebRTC, but some similar technology, and there's like a quarter-second delay, it's difficult to have that conversation with somebody if there's even a quarter-second delay. There's a specific number, I think it's 200 milliseconds, 0.2 of a second, or somewhere in that range, where they say once you have that much delay, this real-time communication, two-way communication specifically, is very difficult to have. Because of that delay, you're always going to be talking over each other. You're not sure when somebody started a sentence, and then you both stop talking, and then you both start talking at seemingly the same time. It's really frustrating. So end-to-end delay needs to be as low as possible. We need real-time streaming. This is very different than what we usually call live streaming. And in fact, for real-time live streaming, I should just say real-time live streaming to distinguish the two, TCP is actually too slow for this. We can't use TCP here. It's one of the few, but the only time in this course where TCP won't be used with the connection, lucky for us, it's only for the peer-to-peer connection. When the peers are talking to our server, it's still going to be TCP. We're still just going to listen on a TCP socket. But once the peers connect to each other, TCP is too slow. That's going to introduce too much delay, specifically when packets are dropped, especially when packets are dropped. So TCP, the whole purpose is reliability, not speed, not performance. TCP is not made for performance. It's made for reliability. Your message will get there. It will get there. Even if the internet's being destroyed, it's going to find a path. As long as there is a path that exists still to get to the other destination, it's going to get there eventually. So if a packet's dropped, we say, hey, you were sending me this message. It's 10 packets. I'm missing packet 5. Can you resend packet 5? And then it just sits there and waits and waits. And then it gets packet 5, and then it assembles your message and then sends your message to you. Well, if that's a few frames in a video call, like, you don't care about that message anymore. After the window of opportunity has passed, like, I don't care about those frames. I don't want to go back and look at those frames anymore. I'm just going to let those frames be dropped and then move on to the latest data. TCP, not the right answer for this. It is suitable for what we call live streaming. If you're live streaming on social media or Twitch or YouTube Live or anything, TCP is perfectly fine there, specifically because the communication is one way. You can allow multiple seconds of delay, and that's perfectly fine. If you're watching a streamer and you're 2 seconds behind, you might not even notice it. But when you have two-way communication, if you're on a video call with somebody, that's when even a couple hundred milliseconds of delay is going to be critical because you have the two-way communication. And that's where we can't use TCP anymore. Twitch, for what it's worth, YouTube Live and Twitch, they both do use TCP to get the messages or to get the streams because you kind of don't want to drop frames. If you're watching a live stream, you don't want to miss anything. If frames are dropped, you're okay waiting a few milliseconds for those frames to come in. That's fine. That's perfectly fine. And you'll be, if you're up to like 5-10 seconds delayed, who cares? I just want to see the whole stream. I don't want to miss anything in that stream. In a video call, drop the frames. Let's keep things going in this conversation. And then I can say, wait, we dropped some frames there. Can you repeat what you just said? And then we'll handle it that way. We'll do our own TCP. So WebRTC uses UDP instead of TCP, something I don't talk about much. If you really want an in-depth look at the difference between UDP and TCP and all the implications of the differences between the two, Modern Networking Concepts, wonderful class. Take it. You'll definitely understand the difference here. For our purposes, I have half a slide on UDP, and that's it. UDP is a really nice, really, I'll say elegant protocol. I don't know if that's really the word I want to use, but it's meant for speed. It's going to get your packets. It might get your packets to the destination. It might not, but it's going to do it fast. It's going to get there quick with minimal delays. And if a packet's dropped, it's just gone. There's no reliability here. And this is very similar to WebSockets in the fact that WebSockets is almost just using the TCP stream. We're just going to use TCP. We're going to add a few bytes of overhead with our headers to send actual messages instead of just streaming data over the connection. We're actually going to have this idea of messages being sent in frames, but we're only adding a few bytes of overhead. UDP is very similar, but with IP. So this is very similar to just using raw IP packets, adding a little bit of overhead for the UDP headers, and then using IP, which is an unreliable protocol. Just send the packets over the internet. If they get there, they get there. If they don't, they don't. Let's just send this data and let it rip. That's my very brief description of what UDP is. When peer-to-peer connection for streaming without server, how to save data, just record the data at the same time. It'd be up to the clients. Yeah, because usually, like, you're streaming on YouTube Live, YouTube's going to store all that broadcast history. That's all YouTube servers, spending a lot of CPU time and everything, hard drive, using all those resources to do that. You can do the same thing peer-to-peer, but you would have to do that. Like, you'd have to either install software that's going to do it, but you're still going to have to use your resources, your CPU and your hard drive to do it. But it'd be up to the peers to do it if that's what you want. And servers are still involved. This is a peer-to-peer connection. So that's what WebRTC is. Servers are still involved. In fact, there's 3 different types of servers that can be involved. 2 of them will be involved, and 1 of them is optional. But 3 different types of servers that we're going to talk about. I'll do an overview here. We're actually going to spill into, I'm going to start Wednesday's slides right away because I want to get into the details after we get through these. So we'll start talking probably at least about the signaling server in a decent amount of detail. And the signaling server is the first of the 3 servers, and this is the one you actually implement in your homework assignment. This is the one that your server is going to be, is a signaling server, and its job is to pass these messages between the peers before the connection is established. So the peers are going to connect to your server. One of them is going to say, I would like to start a WebRTC connection, please. And then you're going to send that to the other client and say, this person would like to start a WebRTC connection with you. And then get the response from them and say, okay, here's, I don't want to go through the whole thing because that's part of the next slide deck. But it'll pass those messages back and forth until they can establish the connection, and then the signaling server's job is done. Next one is the stun server. We're going to need one of these, but we're not going to implement it. A stun server is going to handle the problem of not knowing our public IP and port. We don't know what our public IP and port is. Like if you ask your device, it might not tell you. I think at UB we do. We get our public IP addresses. But we don't necessarily know our own IP address. So the stun server, we're going to ask the stun server, hey, what's my IP address? And it's going to let us know. What's the IP and port specifically that I'm using to connect to you? And it's going to say, here's your IP and port. We're going to use that information to be able to know how we look to the outside world if we're behind a NAT is usually the case, or a firewall. And then finally, the turn server. This is optional, and I think this is the worst. I need a good negative word. I don't know. I don't like it. The turn server is optional most of the time. Sometimes it's required. If you're behind an aggressive NAT or firewall that doesn't allow an actual peer-to-peer connection, the turn server is a server that relays all of the streaming data between the peers. So instead of having a peer-to-peer connection, each peer is going to send its video and audio to the turn server. The turn server forwards that to the other peer, and vice versa, which, for my money, kind of defeats the purpose of peer-to-peer. If you're getting a server involved and it's going to relay all of your data between the two clients, why are you even using WebRTC? Like, I don't really understand this. I get that it does add compatibility. So if your whole infrastructure of your app relies on WebRTC and you have somebody behind an aggressive firewall that isn't going to allow a true WebRTC connection between with another peer, then you can still have that user use your app if you set up a turn server. So I get it in that sense, but it really defeats the purpose of going for a peer-to-peer technology if you're going to use a turn server, because the server's still involved. You better trust that turn server, or why are you using WebRTC in the first place? Like, if you're going to just trust a random third party, just use any other service. Just have a Zoom call. Like, why even bother? And reminder, I just said it not too long ago, but you're only implementing the signaling server. We're going to use a free Google stun server, and turn server, we're not using those things. Screw those things. Details in next lecture, but we're going to get to the start of it today. Do peer-to-peer torrents use a protocol like this? I don't know what torrents use, but it wouldn't use this protocol. I'm not sure what they use. They wouldn't use this because you wouldn't want UDP for torrents, because you need every single byte of data of that file. Or else, like if you're downloading a movie, that movie's going to be corrupt if you're missing even a couple of bytes. You're not going to be able to open the file at all. So it would have to use TCP at some level, or at least something similarly reliable. But I don't know all the details. All right, let's do a demo. So I'm going to start my server. I'm going to go to my server. So the handout code, by the way, when you get the latest handout code for homework 3, in functions.js, this is in the homework doc, but just to make sure I point it out, There's a variable at the top, WS. This is whether or not you're using WebSockets. This is false in the handout. Flip it to true when you're ready to start doing WebSockets. This is going to switch your chat functionality from using polling and Ajax to using WebSockets. And it's going to add this third section of your app right here. So make sure you flip that to true, and then you'll see the Homework 3 version of the app. If you don't see that at all, make sure you grab the latest code from the repo. All right, so the latest code looks like this. I'm going to open this in Opera and Firefox. I'm going to click Start My Video. How's my hair? And there I am, and in the background. I'm going to start my video on both of them. And it'll be, of course, the same exact video. And then when I click Start Video Chat, that's going to start doing all of the WebRTC stuff. And I'm going to have my peer-to-peer connection with myself. And one of them, it'll be hard to see, but one of them should be a little bit delayed. The one on top is the one from this browser. And then the one on bottom is the one that's getting from the other browser. So of course, it's both on my device using the same camera, but the proof of concept is there. This would be a peer-to-peer connection between two clients. And if I go to my server and shut this thing down, we still have a peer-to-peer connection. True peer-to-peer between the two clients. My server negotiated the connection initially, but now that the server has done its job, this is peer-to-peer. I don't need the server anymore. I'm still getting a live video feed. It's streaming between my two clients here. Don't need the server anymore. Peer-to-peer connection. If I refresh, server is down, so of course I'm not going to get the page again. And this, I killed my other client. So the proof of concept is all there. We just showed everything working the way it's supposed to. We expect this to freeze because the other client disconnected. Okay, so that's what we're building. Now, how do we build it? How was I not at the right spot in the website? So let's start talking about the details. We definitely won't get through this stuff, but I want to get through as much of this as we can. Fun fact, torrents were invented by a UB dropout. I think he dropped out before he invented it, or maybe he was inventing it while he was dropping out or something. He was, I believe, a PhD student at the time, and he's like, I'm done with this. But he built something really cool that we all get to use. So I do want to get through these slides. We won't get through this whole deck, but I want to go through the slides, go through the front-end code. There's a lot of WebRTC front-end code that I want to go through, and it takes a while to go through it. And then hopefully still have some time left on Friday to do just generic demos and live coding examples and tips and tricks for all of Homework 3. I still want to do that on Friday. So we'll cut into these slides a little bit and get a little bit ahead today. So hopefully we can free up some time for Friday. Yeah.
So the example you did with Opera and Firefox, if you added to it, that's still working.
No. So let me explain that. I have to give some more background on this one though. It won't work with what we're building on the homework. The homework, you're going to assume there are exactly two connections, and if there's a third connection, if your code doesn't work, that's fine. If there is a third connection, you can still do it, and it was an application objective last semester, and the TAs are mad that I removed it, that to handle any number of connections, and basically have a Zoom call using WebRTC. You can do that, but you do need a connection between each pair of clients. So you're going to have O of n squared connections for all of your users, which is certainly possible. It's a lot of logistics, but it's doable. I had students do it last semester, and it was fine. And I capped it at 4 for the testing requirements, and they had 4 clients all connect peer-to-peer, but each client would have 3 separate connections to maintain. And it was cool, but the students who did it had it was painful. That was, which I might go back to this, but that was when I had 2 application objectives for each homework. So it was like the hard application objective, where the easy one was the one that still remains. So the shorter answer is the technology is capable of it, but you don't have to do it on your homework. All right, so we need to establish a connection. In our homework, our server on the homework is going to be a signaling server, and it's going to negotiate this connection. But how exactly do we do this? How do peers agree to make a connection? So first, you need the IP address of your peer, and then send messages to that IP address, and negotiate the details of the connection. So one client is going to be the initiator of the connection and send a WebRTC offer to the other client and say, hey, I would like to start a WebRTC connection with you. That's what this offer is going to say, and it's going to have quite a bit of information here. It's going to have all of the audio-visual data that we're going to send, the metadata about it that we're going to send, what's the bit rate, what's the codecs we're going to use, everything that you need to be able to make sense of the bytes of the eventual connection. So we're going to send this and say, this is how I would like to send your bytes. So when you do get those bytes, you know how to decode them and actually display them to your human. And a username fragment that's going to be a unique identifier for this connection. So they know who I am, and when I send other messages, they're going to be able to identify me by that username fragment or ufrag. The other client is going to say, sure, let's connect, and send a WebRTC answer back to the initial client. And it's going to have the same information. It's going to say, hey, when I send you audiovisual data, here's the codecs that I'm going to use and the bit rate and all that stuff. And here's my ufrag, so you can identify me. Kind of like we just said, the client might have multiple WebRTC connections. Of course, they're going to be on different IPs and ports. But here's my ufrag. And now we have agreed to connect, and we can start streaming audiovisual data back and forth. So that's what needs to happen. But we can't really do that, obviously, because I just said you need to implement the signaling server, and the server hasn't gotten involved at all yet. So this isn't quite how it has to happen, how it's going to happen, but this is overall what needs to happen. The offer needs to get to the other client, and then the answer needs to get back. And this is part of what we need to negotiate as the signaling server. The problem with this is, how do we just send a message to another client on the internet? How do we do that? Well, for regular web traffic, we type in a domain name or we click a link. Our browser is going to connect to a DNS server and look up the IP address for that domain name. And then our browser is going to send the request to that IP address on either ports 80 or 443, whether it's encrypted or not, for which port to use. This is fine because we have this whole DNS thing, domain names set up, and that's how we connect to devices on the internet that are web servers usually. We don't have the same thing set up for other clients on the internet. Like, you don't have a domain name with an IP address. I mean, you might, but not for your device that's listening for WebRTC connections. You might have an IP address if you're running web servers and stuff. But, or what am I saying? Domain name, you do have an IP address. You might have a domain name if you're hosting websites. But it's not going to be set up for your device to accept WebRTC connections. So how do we do this? And we have a bigger problem with this is our IP import can change. Like, we could set up a peer-to-peer DNS service, kind of like a big old phone book, I guess, and just register our IP import that we like to use for WebRTC and say, here's where you can connect to me. But that's not quite going to work either, because your IP import change all the time. As you walk around campus and connect to different access points, your IP is changing. When you go home, your IP is going to change. And sometimes your IP at home can even change. I don't see it happen too often. I thought it would happen a lot more often than it does in practice. But your ISP can just change your IP address, unless you give them extra money to have a static IP address. but they actually don't change too often, but they can change. So we got quite a few problems, and your port's going to change. Say you do want 2 connections, you're going to need 2 ports. If you want N connections, you need N ports. You'd have to publish and broadcast all them. It's going to be tough. So we have our signaling server. Instead of connecting to the client directly, both clients connect to us, to our server, send the offer to the server, we send it to the other peer, they send the answer to us, we send the answer to the other peer, and they have agreed to start a connection with each other. So this is the first thing that we're going to signal is the offer and answer. We're going to be the signaling server in the middle of all this. So we have a need to send information to these clients. Like this client's going to connect to us, request our HTML, it's going to read the HTML, get our CSS, our JavaScript, all that usual stuff. And then this user's sitting on the page, and then this user sends the offer. They can send the offer with an AJAX request, that's fine. But then we have a need to send this offer to this client who's just sitting there. Enjoying our page. Maybe they're interacting with it. But we need to push a message from the server to the client, preferably in real time. How are we going to do this? Oh, geez, it's convenient that we just did WebSockets. So both clients connect with WebSockets, and now we can use the WebSockets to negotiate all this information that we're going to negotiate with WebRTC. We get an offer. This client has a WebSocket connection open with us. We just zap that offer over the WebSocket connection. It's going to zap this answer over the WebSocket connection, and we just blast it right over here, over that WebSocket connection. This is where the homework simplifies things. We're going to assume there's exactly 2 WebSocket connections to your server when you receive a WebRTC offer or any WebRTC messages. So when you get an offer or an offer or an answer, we're going to assume that it's made for the only other connection on the server. So that simplifies things a bit. When there's multiple of them, you have to say who each offer and answer is for, and there's a lot more to negotiate. Which isn't overly difficult, but I think it detracts from the technology if you're handling the logistics a bit too much. So we get, I already said this, but you get a message over one WebSocket connection, you send it to the other one, and for this one only, we'll restart your server. When we get to the AO testing, we'll restart your server, we'll open exactly 2 windows or 2 tabs, whatever we're using for testing, and then create the WebRTC connection with that. So there will be exactly 2 WebSocket connections for testing on your homework. Okay, but there's another problem. How do we know the IP address and port for each user to connect? We know the IP and port that they're using to connect to us, but what IP and port are they using to connect to each other? They're not going to use the same connection, the same port. They're already using that port to talk to us. So they need to get an IP port combination that they're going to send to the other peer that's going to be available for this connection. And clients don't know their own IP address in most cases. Like I said, on UB, I think you get your public IP address from the network. But at home, you're going to be behind a NAT. Your ISP gives you one public-facing IP address, and then your router is going to have local IP addresses for your local network, which are going to start with 192.168. And those local IP addresses are only for your network. That's not your public IP address. If you say, hey, connect to me on 192.168, you're not getting that connection if the person's on a different network than you. If they're in the same house as you, then yeah, that works. But if they're on a different network, that's not going to work because that's not your actual public IP address. Your public IP address is maintained by your router, and that's what's going to be your IP address to the outside world. So each client needs to know its public IP address. And notice that the port numbers can change here as well. When you have a TCP connection with your router, I should say NAT, your network address translator, when you have this TCP connection open, it's going to say, okay, that's great. I'm going to communicate to the outside world on your behalf, and it's going to choose whatever port it wants. And it has to because you have multiple devices connecting to this NAT, and both 2 of them want to use the same local port number. That's fine for their devices, but the NAT has to have unique IP addresses or unique ports for each connection. It only has one IP address. So this is a NAT. This is a little bit of a problem for a lot of things that we do, that peers don't know their own public IP address. So when we're behind a NAT, we need some way. I got ahead of my slide again, didn't I? So when we're behind a NAT, we need some way to say, hey, this is my public IP and port that you can use to connect to me. This is the one my NAT is using right now. So we need to ask an outside server, which could be our own. Maybe someday you'll implement your own stun servers, which is where this is going. But we're going to connect to an outside server and say, what's my IP and port? How do I look to you? And it's going to say, here's your IP and port. And then we can use that IP and port for our connection. This is the same problem port forwarding solves. If you're behind a NAT and you need to connect using a specific port, especially if you're receiving messages on a specific port, you tell your NAT, hey, if somebody sends a message over this specific port number that, say, Minecraft uses, please forward that to this device. And you might have like 10 devices on your network. Please forward that to this device. That's port forwarding. If you ever wondered what that is, when you have to go into your router settings and add this number in this random place called port forwarding, and then things work. But before that, it doesn't. It's so when somebody says, I would like to connect to your Minecraft server, the router says, oh, that port is being forwarded to this device that's actually running the server. And then your device actually gets the message. Otherwise, getting a message over this public IP address, your NAT isn't going to know what to do with that, where to send it, and it's just not going to send it anywhere if it's not port forwarded. And the short answer is going to be use a stun server. This will be the last slide that we'll get to. But we're going to ask a stun server, hey, what's my public-facing